Welcome back, y'all, to another exciting episode of Arthur Does Math. I'm going to start with my customary apology that I am completely unfocused. My room is a furnace, so, this could be interesting. I have to tell you a little bit of a side note, but I'll tie it back in, I promise. A little bit of stream of consciousness here. So I was looking at these notes that we were filling out, and we're going to talk about solving trig equations, if you can't tell by now. And this first line said, remember, first quadrant of the unit circle. And I'm not going to lie. My first thought was, why, yes, I do. Now what? I honestly have no idea what I'm supposed to put here. It's kind of interesting. I don't ever make these notes. I just use them because another teacher makes them, and they're great, and they're helpful when I'm not here. But I probably should ask her about them. Maybe we'll draw the first quadrant. But anyway, I was thinking, there's got to be a more interesting way to start a unit circle lesson, because we've been looking at that circle forever, and we're going to keep looking at it forever. So I was already on YouTube, and I just decided to type in unit circle and just see what came up. Well, you know how they always have suggestions for what you're typing in, and first suggestion that came up was unit circle song, and I was like, heck yeah, there's a song about it, which I don't know why I should be surprised. There's a song about everything, and boy, let me tell you, there are a lot of songs. I have literally just spent the last 20 minutes of my life listening to unit circle songs. The first one that had like 200,000 views and was probably the most popular one should have been an indication that I should have stopped there. Okay, because if that was the most popular one, I probably wasn't going to get any better. But I kept clicking. Curse you, YouTube. Whatever YouTube has created is a beast that cannot be contained. You cannot just watch one YouTube video. It just doesn't happen ever. And so, because of that, I would like to share with you my favorite of them. I feel like many of you could relate, just to kind of set the mood for this lesson here. So enjoy the first 15 seconds of Unit Circle Song.
I forgot the unit circle, radians and degrees. I forgot to study MIAs with down to B's. I forgot the top half goes from 0 out to pi. I forgot it all, and that's no lie.
Isn't that just the best thing ever? Like, that's the intro to the song, and then he just starts singing the coordinates and stuff, and yeah, go look it up. You can waste 20 minutes of your life too. Anyway, we should probably get on to the notes so I don't make another 40-minute video. So, focus time. First quadrant of the unit circle. It's a really good thing to know. We've talked many times that if you know the first quadrant of the unit circle, then you can find through reflections the rest of the unit circle. And since we spent all this wonderful time to make a unit circle, I'm not going to draw this back in here. I'm just going to stick with yes and move on, and if I feel like there's more that you need to see later, we'll come back to it. Okay, so there's an important note here that oftentimes when I do these notes, we tend to not read what's there and we just fill in the examples. So I'm going to read it to you so that you actually look at it. It says, when we solve a trigonometric equation, we are looking for all angles which make a statement true. So I know it's bolded, but where bold is good, underline is better. All. Okay? Because the trig functions are periodic, there are infinitely many angles that would work. To make things a little easier on ourselves, we typically restrict our solutions to x's greater than 0, greater than or equal to 0, and less than 2 pi. Notice that this here is not a less than or equals, because 0 and 2 pi have the same measure and the same coordinates. So we approach 2 pi, but we never hit it because we've already covered it with 0. And so then you can see the domain written here in interval notation as well. And there's a serious lag on my camera, so that's weird. Okay, it's not keeping up. Anyway, so remember that property of periodicity that we talked about. You can find infinite number of angles with the same values. And so we're just looking at 0 to 2 pi. I don't know why I had to repeat that. It makes me feel more important if I repeat things many times. So the first thing says find all values of x between 0 and 2 pi that make the statement true. Now I want you to notice this is very different than when we did the inverse trig functions. Okay? You might think, just looking at this, that, oh, well, to undo the sign I need to do the sine inverse, and then if I take the sine inverse of 1/2 it's going to tell me what x is. That's not the question though. Okay? We are not using that inverse function. As we talked about recently, the sine inverse and all the inverse trig functions have very restricted domains, and they do not give you all of the angles that could make this true. So it's actually better to rely on your knowledge of the unit circle, as much as that might scare some people and as much as you might relate to that little intro song, than to rely on technology. Alright? So I want you to get your unit circle out. I have mine. Ta-da! Looks nothing like yours. Yay! But I'm really proud that I made this in 2013 and I still have it. If you've seen my desk, you know how much of an accomplishment that is. So I'll be referring back to that later. So let's think about what angles have a sine value, or in other words a y coordinate, of 1/2. Okay? So if we look at that, it's as simple as saying that x could equal pi over 6. Do not put degrees. Okay? X equals pi over 6, or x can equal 5 pi over 6. And I think I could just put a comma between them instead of an or. But both of those make the statement true. And that's it. Like, moving on. Okay? What about the cosine? What angle value would give us a cosine of -1? Or in other words, when is the x value -1? So there's not always 2. This one, there's only 1 between 0 and 2 pi. It's when x is equal to pi. Okay? The cosine value of pi is -1. Alright, let's look at the cosecant. As infuriating as that might be, we're going to look at the cosecant. Now, we got to remember that the cosecant is the reciprocal of the sine function. So I'm going to write that here. I'm going to say the cosecant of x is equal to 1 over the sine of x. Alright, which is still equal to 2 over the square root of 3. Well, there's this cool property of fractions that hopefully you learned somewhere in your life that says that if two fractions are equal, then their reciprocals are also equal, and you can pretty easily verify that just with some scratch work off to the side. Scratch work square. So like if you have 1/2 and you know that that equals 13/26, just because, then it is also true that 2 over 1 is equal to 26 over 13. Okay, both of those just equal 2. Because you're keeping the relationship between the two numbers the same. Okay, they're still 2 and 1 are still together, just in a different order. And I don't know where I'm going with that. It's pretty self-evident. I'm sure it has a fancy name that some mathematician thought up that I don't know. But what we can use that for, though, is I don't know anything about the cosecant. We didn't write that on the unit circle. But I do know something about the sine. But I don't want 1 over sine. I just want sine. So let's flip the sine, the 1 over sine. But then I'm also going to keep it equal by flipping that result. Right? So this is the same thing as saying that the sine of x is equal to the square root of 3 divided by 2. And that one we know. Okay, we're going to go to our unit circle and find what angle has a sine value, or a y coordinate, of root 3 over 2. So x equals, what is that doing there? Alright, pi over 3. I'm just going to put a comma. I don't think we need an or. And a 2 pi over 3. Okay? And that's it. I mean, there's really very little work to show on that. Moving on. So you get some homework questions like that. Those are not too bad. However, we can also solve equations that don't involve a nice unit circle value. So to do that, though, we're going to need technology. And there are two ways you can do that. You can use the inverse trig functions, or we can use the graph. Now, personally, I think the graph is easier and a little bit less confusing. Maybe not quicker, though. I'm going to show you both. Please feel free to stick with one that you like best. So let's do the what did it list first? Inverse trig. All right. So this is inverse trig on this side. So so this is where, like we assumed earlier, you can take the cosine inverse of both sides. Alright, so if I have the cosine of x is equal to 0.75, I can use the inverse operation to eliminate this cosine, so cosine inverse. And I can do the same thing on this side, cosine inverse, so those cancel. And I'm left with x equals the cosine inverse of 0.75. So let's come here. Always check your mode. We need to be in radian mode. Okay, everything we're doing, since my domain is from 0 to 2 pi, that tells you right away I've got to be in radian mode. And since my other classes are also doing trig, they are putting the calculators in degree mode. So if you're borrowing one from me, please double check that it's in radians. Also just check your own personal ones, because that is the fastest way to get a wrong answer. To do everything right and still get it wrong. Okay? So let's type in the second cosine of 0.75. And it gives me 0.723 since we're going to go to 3 decimal places. So x is equal or approximately equal to 0.723. However, that's not the full story. As you know, for almost any value, unless you're on the axes, you're going to get two cosine values. So we kind of took this out earlier for time, but if you think about the unit circle and cosine, cosine is the x values. So 0.723 radians, that's, I don't know, somewhere over here. And again, we didn't talk about estimating radians as a decimal. If you think about it, though, there are pi radians in half a circle, which is roughly 3 radians. So 1 radian every third, so this is probably a little too high. But it's somewhere over there. So if I want to find another angle that has the same value of cosines, because again, I'm solving this original equation. This was a step to it, but not the full story. That means that I want an angle, let's use red. I want this angle down here, okay? Because they're going to have the same x value. One has a negative y value and one has a positive, but that's not what we're asking. So to do that, the simplest way is to draw this picture and say, okay, I want to go backwards this far, so what if I subtract 0.723 from 2 pi radians, since 2 pi is the full number of radians in a rotation? So I would say 2 pi minus 0.723, ask Mr. Calculator over here, 2 second pi minus, alright, that's bugging me. That's better. 0.723 tells me that my other radian measure would be 5.560 radians. Equals, get out of here. Wait, come back, I don't remember what you said. 5.560. 5.560. I'm going to keep that 0 there, I think I've said this before, to imply that there are more decimal places, but that I was rounding to 3. So, my two answers are this guy and this guy. But again, that requires you to do a picture, that requires you to know a little bit about cosine, that it's the x. I mean, I feel that it's not as clean. There are some rules you can memorize for what to subtract from for cosine, but it's different for sine and tangent and all that. So I think a more generalized method that you can do is the graph. So here's the graph method. Okay. The graph method is that we are going to, into our calculator, in y1, we're going to graph the cosine of x function. And in y2, we're going to create a horizontal line at 0.75. And then, as we've done before, those two will be equal when their graphs intersect. So, y equals, let's do cosine of x, and 0.75. Now, I could hit graph here and it would work, but I want to make sure that I don't repeat more values than I need. So I'm going to change my window real quick. Instead of my x min being there, I want to start at 0, because my domain, as you can see up here, is 0 to 2 pi. And then I'm going to come down to my max, and I'm going to do 2 second pi, and it will automatically change it to a decimal. Whatever, that's fine. I also know that the cosine doesn't get that tall. I'd like it to look like a cosine graph instead of like a squished worm or whatever. So I'm going to make this -2 and this just +2. And then my graph looks nice and something we're used to seeing. I was going for a song there, it didn't work. Okay, so there's two places, as we would expect on the unit circle, where these intersect. So we're going to go second, trace, option number 5 for intersect. It's going to want the first curve. Okay, I'm already selected on it, but I'm going to move over. First curve, then it jumps you to the second curve, hit enter, give it your best guess. The one you guess closest to will be what it finds. Hey look, 0.723. What do you know? So, I mean, if I really wanted to get technical, y1 equals y2 when x equals 0.723, and also x equals, I'll let you know a secret, I bet it's 5.560. Just a hunch I've got. Second, trace, option 5. Gonna be waiting. Okay, first curve, second curve. Best guess. The more accurate the guess, the more accurate the answer. Hey look, 5.560. What do you know? As you can see from the amount of writing, the graphing method's probably a little bit more straightforward. Again, if you're really familiar with your unit circle, you could probably do this one faster, but for now I don't necessarily recommend it. So the tangent, we're going to do the same thing. I'm just going to go with the graphing method. I'm going to graph the tangent of x, and I want it to equal -0.79. Graph it. Okay, two more places as we would expect. Also notice these marks are still 1, 2, 3, 4, 5, 6, and so on. If you wanted to make it look like the marks that we've been doing when we hand draw these graphs, you can go into the window and let's just do it. You can change your x scale, so instead of counting by ones, I can have it count by pi divided by 2, which is what we normally do. And then you've got nice marks where we're used to seeing them, and then the tangent goes through pi right there. There we go. Alright, so second trace, option 5 for intersect, first curve, second curve, best guess. It's really hard to see. 2.473. So honestly, for work, I would want to see something, you know, sketch a graph. Here we go. Like that. And then here's my line down there somewhere. Should have done this on the other one. Okay, just a rough sketch. And then I would say x is equal to 2.473, comma, let's do the other one, option 5. I know you can't see it, nor do you care to see it. I've decided to jump down to the red line to move over. It doesn't matter which one you make, you know, your first and second equation, but there's first, there's second. And there's the intersection, 5.615. 5.615. We're done. Okay? Pretty simple. Just make sure you're in the right mode. If you're in degree mode, it's going to throw it all off. So, did you know that we can also use algebraic techniques to help us solve more complicated trig equations? I did. If you care, I did. I knew that. So, 2 sine of x minus 1 equals 0. Very similar to when we solved logs, when we solved radicals, when we solved exponentials. You want to isolate the type of function that you're dealing with. I want to isolate the trig function here as much as possible. That means moving anything that I'm adding or subtracting to the other side of the equation, getting rid of any coefficients, stuff like that. So I can easily add 1 over here to both sides so that I get 2 sine of x equals 1. And then I can also divide by 2 to clear out the coefficient. So I get the sine of x equals 1/2. I believe we already did that one. Hey, look, we did. It's pi 6th or 5 pi 6th. Okay, and again, it's saying all solutions in that interval. So x has to equal pi over 6 or 5 pi over 6. And that's it. We are flying. Might only be 30 minutes this time. Actually, I'm getting close. I started at 8:15. It's 8:40. So, here's another one. Now, this one, you can't really isolate the trig function on its own. Yeah, you could, add the 1 and factor out a cosine, but then you still have 2 factors with the cosine, and that's not what we want. So I'm hoping by now, since we've done a couple of sections on it, that you recognize this is a good candidate for u substitution. Okay? I've got something being squared, and then I have that same something just by itself. So if I let u equal cosine of x, that means I can write this equation as 2u squared minus u minus 1 equals 0. We can factor this. Okay, we're probably most comfortable with a box method type thing. So this is 2u squared, this is negative 1. Okay, I need factors that multiply to be negative 2 and add to be negative 1 in there. So that's going to be negative 2 and positive 1. So negative 2u and then just a positive u. Alright, so I get a 2u and a u and a 1 and a negative 1. So this thing factors as 2u plus 1 times u minus 1 equals 0. So that means that u is, okay, I would subtract 1 and divide by 2. So u is negative 1/2, and u is also positive 1. So we need to replace the u value with our original substitution, so we put cosine back in. So the cosine of x is equal to negative 1/2, or the cosine of x is equal to 1. Alright, so we look at our unit circle, or just what you remember. This one is going to be 2 pi thirds, so x equals 2 pi thirds, but it also equals 4 pi thirds. All right, then we do the second set. So there are equations like this because of the nature of cosine and its periodicity that there are more than two answers. You can have 4, you can have 6, you can have infinite number, really. So the cosine is equal to 1 only when x equals 0 radians. Okay, so altogether, I have these. Now, it's not a bad idea to go back in and check. Just saying. Yeah, because, I mean, they're going to work, but you can always plug them back in and see what you get. All right, best for last. Who's excited? So, here I've got 4 cosine squared of x times sine of x equals 3 sine of x. So, I really want to separate these, and since these are being multiplied, the best thing I can do is divide by the sine of x on both sides. But it's going to give me the same value no matter what x is. When I take the sine of it, it's going to give me the same value, so this cancels, but this also cancels over here. That was nice. So 4 cosine squared of x equals 3. I'm going to divide by 4 to clear out the coefficient. Cosine squared of x equals 3/4. Please do not take the square root early. Alright? The squared is only being applied to the cosine, so I only want to take the square root of the cosine, not the coefficient in there as well. But now, since it's isolated, we'll take the square root of both sides. So I get the cosine of x is equal to, now, since I took the cosine, alright, it wasn't there to begin with. I do need to include this plus or minus here. Alright, especially since it's being squared here. So whatever the value of the cosine is, whether it's negative or positive, when I square it, it's going to come out positive. So I have the option of letting cosine x, not the option, but privilege, not even close to the word I want. I hate English, whatever, we're going on. I need to make sure that I account for both of them. So remember that I can split up my square root, and so this becomes plus or minus the square root of 3 divided by 2, since if this helps, square root of 3 over the square root of 4. Okay. So I need all the values, all the angles who have cosine values that are either 3 pi over 2 or negative 3 pi over 2. So x is going to be equal to pi sixths. Okay. And then let's just stick with the positive ones. So it's also going to be 11 pi sixths. Oops, 11 pi over 6. Alright, then if we look for when it's negative square root 3 over 2, we also have 5 pi over 6. And finally, 7 pi over 6. If it really bugs you that those are not in descending order, deal with it. Or rewrite it. Have at it. Just pause it right now, rewrite it. I'll wait. Okay, great. Example 4. A heater turns on in a home when the outside temperature is below 45 degrees. Who the freak are you? That is cold. My heater turns on like the instant it drops below 60. Man, freaking Eskimos or something here. During the middle of March in Salt Lake City, you can model the outside temperature in degrees Fahrenheit using the function f of t equals 43.9 plus 9.5 cosine of pi over 12t, where t is the number of hours past noon. During which hours is the heater heating the home? Cool. So, anytime you start to see weird numbers like this, that if it's not on the unit circle, we don't expect you to do it by hand. You need to approach it using a graph. Okay? You also need to talk some sense into these people. Sorry, I hate the cold. We're going to graph this thing. Alright? Notice that t is the number of hours past noon. So we're not really going, well, okay, during which hours is the heater heating the home? I take that to imply that we're starting at noon and we're examining after noon. I guess we could go into the negative range. That's open for interpretation, and I am interpreting it as no. So let's go and let's graph this thing. Y equals. So 43 plus 9.5 cosine. I do want to put parentheses. No, it's already got parentheses. Never mind. So we use the pi button. So you hit second and then the exponent button. You get pi divided by 12. And then the t is on the inside. And we're using x here. Okay, t was for time, but ours is x. I know it's kind of, it's implied that the t is in there. If they wanted it multiplied by t on the outside, they would have put it at the beginning. So there are implied parentheses here. Now, I want to use the same technique as earlier and draw a second line and see when we're greater than that. So it's only going to turn on when the temperature is below 45. So my second line I want to be at 45. Now I'm going to have to play with my window here. Notice that I am adding 43 to this. So my midline here is at 43. So when we go, no, let's go to window. I can still keep, I think I'm okay with the x's there for now. But my max, let's call the max 60. And the min, it's March, let's be reasonable here. 32. You could stay with 0. I'm just trying to get it so it looks like a decent graph, which obviously I failed at. Okay, so look at what's happening here. We expect the cosine to complete a cycle, okay? But notice that this one hasn't completed its cycle at all, and part of that is we come in here looking at the b value. So I should have probably checked for my period first. Remember that period is equal to 2 pi divided by b. Well, if I put that in as 2 pi divided by pi over 12, it's the same thing as saying 2 pi times 12 over pi, which means that the pi's are going to cancel and I'm going to end up with 24, which makes total sense because there's 24 hours in a day. I'm a little slow. I should have seen that earlier. But regardless, when you're graphing these, you really want to make sure you get the full cycle so that if there's any repeats, you know, I feel like this line's going to intersect the graph again. So my window, instead of my x max being 2 pi, we're going to make it up to 24. Hit graph. That's looking a little better. Ooh, it stayed above freezing. There you go. So as usual, you should know by now, I want a little sketch. Okay, and I probably shouldn't have put the axis here, because if I make this 0, then I'm way up here. And again, I'm not too picky about the graph. I just want you to show me that you know what you're doing and that that's how you did it. And then there's a line that's kind of like that. Totally good enough for me. Okay, let's find the intersection points. I want to know here, and then the question says when is it below? So I'm actually looking for all of this stuff down here. Okay. Nope, that's not what I wanted. Graph. Second, trace. Option number 5. Let's find where it starts. Enter. Second curve. Find the intersection. Okay, so when x equals 5.190 because of the rounding. this, I'm gonna just let's do this. I like this one idea better. This is at x equals 5.180, and then the second one, trace intersect come on, you can do it. There you go. And this is at 18.810. So it is between those hours after noon. So we could make our lives super miserable by trying to figure out exactly like what time of day that is. Which if I were really mean I would make you do, but this video is already long enough and that's not what we're doing. So if you craft your answer carefully, we can answer the question without actually fully answering the question. So what I mean is we can say something like the heater is on from 5.180 hours to 18.810 hours after noon, right? What you doing there, N? There you go. So that means that whoever's reading this, if they really want to know what time, we've given them all the information to figure it out. We just haven't done the legwork on it. And I think that's good enough for now. You get the idea. Okay, so just craft your answer carefully. Make sure there are units included. So I put my hours in there. And we're good. We could also probably say the same thing using interval notation. Notice that the problem says below 45, not at 45. So if I were going to put this in interval notation, I would say from 5.180 to 18.810 hours after noon. It's probably a more concise way of putting it, that one on the bottom. I like that. Go me. Okay, any questions? None? Good. Go forth and conquer. Alright, good luck on the assignment. We will go over any questions that you need next time in class. Thanks for watching. Sorry I didn't make it under 30. Have a good day.